Welcome to Fourth International Congress on Human-Computer Interaction, Optimization, and Robotic Application. The Congress aims to bring scientists, experts, instructions, non-governmental organizations, and private sector representatives together to share and discuss theoretical and practical knowledge in a scientific framework. In addition to cutting-edge research paper presentations in human-computer interaction, optimization, and robotics areas, the Congress serves as a multidisciplinary platform for discussing current issues in the engineering areas. FORA 2022 is organized by National Technical University Kharkiv Polytechnic Institute. FORA 22 is technically sponsored by IEEE Turkey session. Thank you for your scientific contribution and support to FORA 2022. If you want, let's start the first session of the symposium. First paper belongs to Abdurrahman Abdul Wahab Al-Ahami. Are you ready?
Hello. Hi.
Are you ready?
Yes.
Okay. Okay. You can start your presentation, please.
Okay. Open my camera.
You can share your screen.
Okay. Okay. It's okay.
Okay. You can. You have 10 minutes, please.
Sorry.
You have 10 minutes. Okay.
Okay. Robot path planning with avoiding obstacle in known environment using area segments and the obstacle classification. Introduction. Background. Robotics today are integrated into the modern environment in automated production system where manipulative robots are used in commercial and industrial activities to maneuver or have a variety products available. On the other hand, mobile robots have other methods of operations such as obstacle avoidance, line trackers, and mobile explorers. These robots are required to have a demand due to their high complexity in their operating system. Since they are used in the research methods. For this reason, we propose a vision system whose main purpose is to detect and avoid obstacles and known environments by deploying future extraction and classification algorithm DNN of obstacle and RGB deep images. In the figure, we can see the robot detected obstacle through computer vision. Next problem: obstacle detection and avoidance are two main problems that demand solutions in the autonomous movement of mobile robots. To this end, the robots have been equipped with the seasons and cameras. The purpose is to increase the robot robustness, dependability, and independence from a human. And involvement autonomous robots must be designed in such a way that human health and safety are protected as well as the environment and the robots functioning. This figure shows how the robot avoids obstacles to reach the target. Next slide. Contribution. The main contributions of this study are summarized as follows. An effective method based on a molecular camera that can be used to avoid collision has been proposed. The mobile robot is capable of navigative by avoiding obstacle in a known environment. Science obstacles are not detected separately. Obstacles avoidance is achieved quickly and easily without the need of additional filters. Kenny, Sobel, and Lablicans. Thus, the calculation are performed at a low cost. To our best knowledge. This is the first study that use the KNN to find simulators or difference between segments. Next slide. Materials. Robots, mobile robots are grouped into four groups based on their mode of transportation: land, sea, air, and space. The collection many physical and computational computed include energy source, movement machines, mechanisms, and sensors. Mobile robot system may be implemented in a variety of locations, including the home business, and industrial robots. Industrial robots are essential for labor and in hostile or dangerous environments, as well as instances where sending a human would be prohibitively costly and time consuming. Automated system may also be advantages and respected tax the operators physical and mental capabilities. Next slide. This table shows the types of robots we will work on the omnidirectional robots. Next slide. Obstacle avoidance. Mobile intelligence. Robot is a useful tool which can lead to the target and at the same time avoid obstacles facing it. There are conventional methods of obstacle avoidance such as the path planning method, the navigation function methods, and the optimal regulator. The first algorithm that was proposed for the discussion of obstacle avoidance, and this is the bug one algorithm. This algorithm is perhaps the simplest obstacle avoidance algorithm. In the first algorithm, bug one, the robot completely bypassed the first object, and then it leaves the first object and performs at the shortest distance from the target from the target. Of course, this approach is very efficient, but it ensures that the robot is reachable for any purpose in this algorithm. The current sensor reading play a key role. The weakness of this algorithm is the excessive percent of the robot algorithm. Robot alongside the obstacle. Next slide. This figure depict the segmented areas. Next figure. Next slide. Area segmentation. Mobile robots must be able to move freely in the known or unknown environment by avoiding obstacles. Detecting and avoiding obstacle are among the most important and challenging issues to be considered in safe navigation. Virus methods have been proposed to solve the obstacle avoidance problem. Some approach use laser sensors, and some use ultrasonic sensors. In addition to sensors, vision based methods are also used to avoid obstacles. Next slide. This figure shows how FCM segmentation work. 17. This is the outline of our methods. Proposed methods. This is the outline. And this study FCM for segmentation semantic segmentation is briefly reviewed compared with the classification and detection. Takes segmentation is such more default task. Second, image classification. Classify the object, recognize the object class within an image. Third, object detection. Classify and detect the objects within an image with bounding boxes. Bound the objects that means we also need to know the class position and size of each object. Fourth, semantic segmentation. Classify the object class for each pixel within image. That means there is a label for each pixel. Fifth, search for optimal path using PSO search algorithm. Next slide. This is outline for our methods. Next slide. Modeling the 3D area. The robot takes a snapshot every 5 centimeter. This is how the robot would divide the surrounding environment into safe and harmful zones based on the plant size at the moments of division. Following image analysis PSO determines which brushes of the picture are safe based on the and the result of the FCM algorithm. This three-dimensional habitat was produced using Autodesk Maya and MATLAB software. The dimensional space is used to depict the surrounding. Next slide. The design of our environment in the 3D software. Next slide. A screenshot of the front camera of the robot. Next slide. Accuracy result. Despite the fact that the PSO KNN might not be the most accurate classification system, the figure below indicates that it takes that the last amount of time to try and make choices when compared to other classification system. Next slide. The accuracy of our model compared to the work. The next slide. Conclusion. This is the outline. This study proposed a new image based floor detection approach in an indoor environment for autonomous mobile robots. Obstacles were detected using image segmentation and KNN classification. Second, however, it should be noted that even if the obstacle and the wall are similar, the obstacle can easily be separated from the wall. Third, additionally, as the proposed method does not require any prior knowledge of the environment. It can be applied to real-time problems. Fourth, the experimental result show that the proposed algorithm reach 89% accuracy with the limited time compared to others with higher accuracy and too much time. Hence, it can be concluded that the proposed provides successful result at a low cost, without the need for additional filters that are used in the processing. That's it. Finished.
Okay, thank you for your presentation.
Okay, thank
Dear
you.
participant, do you have any question about the paper?
No, I don't have any question.
Okay, thank you again. The next paper
Thank you for you.
belong to dear Akansel Coşkun. Are you ready to present?
Yes.
Okay. If you want, you can start your presentation.
I think if the previous presenter stops sharing, then I can share my screen.
Okay.
Okay, that should work.
Please, you have 10 minutes.
Sure. Just give me a second, please. All right. Can you see my screen?
Yes.
Okay, thank you. Yeah, this paper is called Shared Control Robotic Manipulation in Virtual Reality. I'm Akansel Coşkun from Monash University, Melbourne, Australia. And this work was mainly conducted by my students, Shiyu Zhu and Scott Moore. So introduction, the ultimate goal of robotics is, as we know, full autonomy, right? The robots to work autonomously. But however, some of the robotics technology is still not mature enough for many of the applications that we like to do, right? So the idea is of teleoperated robots is remotely controlled, human robot control, make some applications, robotic applications feasible. If you look at the state of the art, we see that the standard of teleoperation methods include either standard mouse on keyboard interfaces, like controlling the robot using interface on a computer screen or using some sort of joystick. And the idea that we explore in this paper is, what if we wanted to use virtual reality for teleoperation? What if we were to project the sensor information into the virtual reality? The contributions of this work is twofold. One is we have integrated the Meta Quest 2 virtual reality headset, the Fetch robot, for successful remote manipulation application. And we also released the source code of the project so that other researchers who are interested in this work can replicate our work. To define the problem, we have a robotic arm. So this picture depicts the Fetch robot. The Fetch robot is actually a mobile manipulator. It has a mobile base, but we do not use the mobile base. We only use its robotic arm. And we have some objects on the table. We have a user that's at a remote location who wants to control the robot. This remote user is wearing a Meta Quest 2 virtual reality headset, and the right bottom we see a typical VR view what the remote user is seeing. So the problem is how do we design the interface, the interaction, so that we share essentially a shared control, right? So that the user do not control every aspect of the robot. So there is some autonomy that helps out the user to carry out the task, to be able to manipulate objects in the environment. And in this particular, here's our approach. As I said, we use a VR headset, a Fetch robot, and there's an RGB camera at the head of the robot. So we visualize the sensor data in two forms. We project the point cloud into 3D space, and we also show the video stream projected to a wall in virtual reality. So the control happens by the remote user choosing and setting the next waypoint, where we define the waypoint as a position and orientation of the robot's hand, the end effector. And we check for the feasibility for the next waypoint and communicate that via visualization to the user, whether it's feasible or not. And then in the back end, we use a general purpose move motion planner to check for feasibility and to move the actual arm. I'll go into details. Just to talk about the task on the up, we see the actual image. We have a table and we have an object that you want the robot to manipulate. It's a Rubik's cube in this example. We have a container, and as you see, the robot is there. The task is to essentially grasp the Rubik's cube object and put it into this gray container. On the bottom, we see the VR, what the remote user is seeing. So we project the point cloud onto the virtual table, and we project the video onto the wall, and we also project any message to the user to the wall as well, so the user can check the log. This is also another example. So just for example, we place 3 objects on the table, and on the right you see what the point cloud essentially results to. I would like to mention that we also provide object segmentation and cleaning up of the point cloud, so that we don't show redundant information to the user. We only show the objects. So motion planning. Motion planning is responsible to solve for the joint positions of the robot arm to go from one robot configuration to another robot configuration. In our design, when the user moves the controller, we visualize the robot's end effector in that location, but nothing happens until the user presses a button. So when the create plan button is pressed on the controller, we check for the feasibility of that end effector configuration. If this position, if this pose is feasible, then we display the end effector as green. If not, we display it as red so that the user knows if it's feasible or not. In the back end, we use, again, MOVEit, which uses RRT star for motion planning. So if a feasible trajectory is found, then the user can press another button, which is for executing the trajectory. Then the actual robot arm moves. So the idea is to have the human-in-the-loop control to do this iteratively multiple times until the user reaches a goal position, a desired position. We also have another button on the controller to essentially close the gripper and open the gripper accordingly so that the objects can be manipulated. This is an example of the virtual view of what happens, for example, for instance, if the user presses the button to create plan. So when the button's pressed, since these algorithms take some time, the planning algorithm, while planning is underway, we show a blue end effector as shown on the left. And if the plan is successful, we show this plan, the pose as green so that the user can execute the trajectory. Otherwise, we show it as red. So the user has to essentially try for other poses. So there are reasons why there is, the plan might not work. There might be kinematic infeasibility. The op might not be physically able to go there, go to the desired location, or there might be obstacles on the way. So we essentially had a demonstration where multiple users were able to execute a remote pick and place task that I described for Rubik's Cube and the gray container. I'd like to show a video. If I can increase the resolution and start again. Hopefully this works. Yeah, on the right, the larger screen, you see the virtual environment. On the leftmost, you see the actual robots. So what the user is trying to do at this stage is move the arm to be able to pick up the Rubik's Cube. And the user is essentially trying to find feasible arm locations. And then the arm will descend and go to a position to pick up the cube. The user sometimes use the point clouds, sometimes use the video stream, then moving on top of the container and opening up the gripper. So there are limitations to the current work. For instance, sometimes the visualized point cloud is incomplete. And that's because, for instance, the robot arm itself might block the view. It might come in between the RGB camera and the object of interest. So there are ways that we have thought. For example, we can move the arm more intelligently in a way that doesn't block the view, or we can detect the objects on the table and show their 3D object models, for instance, that will help with the occlusions. Or we can combine multiple point clouds from multiple viewpoints. However, this will only work if the robot is stationary and if the robot is not mobile. The other limitation, main limitation, was that essentially the user tries for checking the feasibility multiple times, which is time consuming. A single manipulation action takes a long time, even for trained operators. So the idea is, in the future, if we can add more autonomy to suggest kinematically feasible options to the user before the user tries them. To conclude, we have found that the work to integrate the system was actually a lot of work, and the remote teleoperation was difficult and slow, rather slow. This is why better and more careful user interface design is necessary for simultaneous interaction for this task. Our approach was a first step towards this direction. We have utilized a virtual reality headset for shared autonomy. There is some autonomy, but there is human in the loop as well. And we think that VR presents a high potential interface for robotic teleoperation. For future work, we have some ideas. We'd like to expand this type of operation system to any kind of robotic manipulator. So there is a common interface to move these robots. And we like to add mobility. So we like to essentially enable the user to actually move the robot arm to another place. Then you'll have essentially VR-based navigation and manipulation, which will help to tackle a more diverse set of tasks. And we'd like to conduct user studies to determine whether people, novel users, are comfortable with our UX design, and to also determine what is the best autonomy level for this task. Also, a plug, if you're a student who are interested in doing intelligent robotics and would like to do a PhD in Australia, you can reach out to me from this email. Thank you.
Thank you for your presentation. Dear Parson, do you have any question about this study?
Yeah, I have a quick question, if I
Okay.
can.
Sure.
Yeah, I like the presentations, the idea, I mean, here for the virtual reality. In terms of the robotic gripper, I mean, in terms of the grasping, have you tried, I'm wondering, have you tried any other, gripper for this specific issue?
Well, we only tried a parallel gripper, which comes by default by the Fetch robot. However, I think it's, for example, if we had like a vacuum gripper or more like a multi-fingered hand, it will be, then the user might need to have, or we might need to have add more autonomy to plan for the fingered motions, for instance. So we deliberately used a simple gripper for proof of concept, but I think it's a interesting problem how to tackle this problem with a different gripper. Yeah,
you are right. Because from my side, I work on the soft robotic grippers. Maybe it could be great to try, this kind of gripper in this issue. Yeah,
interesting.
Maybe in the future.
Thank you for the question.
Yeah,
thank you.
Okay, thank you.
Any other questions or?
Okay,
well, thank you for the opportunity.
Thank you for your presentation again.
Thank you.
I wish you success in your career.
Thank you.
The next study belongs to Omar Al-Mutalbi. Dear Omar Al-Mutalbi, are you ready? Okay. Mr. Savaş Dilibal, are you ready to present? Okay. Maybe your voice is.
Oh, yeah.
Okay.
Can you hear me now?
Yes.
Yeah, sorry, my voice was off. In this study, we worked with close collaboration as Gedik University with Sant'Anna Biorobotics Institute from Italy. And I'm going to present grasping of lithium-ion batteries via additively manufactured soft gripper and collaborative robot. If I continue, yeah. Can you see my next slide now?
Yes, please.
Okay, great. Yeah, the use of lithium-ion batteries has dramatically increased in the novel mechatronic systems, such as electric vehicles, drones, e-bikes, and grid-scale energy storage. Due to the increased demand in the lithium-ion battery cell in the industry, an efficient robotic automation system is needed for the battery manufacturing and integration companies. A large-scale battery pack consists of many battery modules connected in series and parallel combinations to increase battery capacity. And in each battery module, there are several numbers of cells wired in series and parallel connections. The battery module manufacturers design the series and parallel connection of the cells based on the desired module capacities. In industry, lithium-ion batteries are in the form of coin, cylindrical, prismatic, and port formats with different capacities and sizes. The cylindrical cell is the most widely used package type due to its standardized sizes and simple manufacturing process. Standard cylindrical cells are the most commonly used battery in application. In the literature, you can find some of the disassembly automation of the lithium-ion battery, as you can see on the slide. And the packaging and pick and place of the lithium-ion battery cell can be also found in industry with metallic gripper jaw system. However, soft robotic grasping for lithium-ion batteries has different advantages. These are reducing the damaging risk of the lithium-ion batteries compared to the rigid gripper, self-insulated soft robotic gripper for pick and place tasks, easy integration process with the collaborative robots, coherently work with collaborative robots in active and passive missions. In this study, we worked on a FANUC collaborative robot with a 10-kilogram payload, and we have developed a 2-finger soft pneumatic gripper, which is additively manufactured and integrated to cobot system. And a silicone layer has been bonded on each finger surfaces for soft grasping. Here you can see the application-based 2-finger soft pneumatic gripper. And in terms of the control system, you can see the 4 steps. These are pre-shaping, closure, grasping, and releasing. And the flow diagram of the proposed control system can be seen on this slide. And when it comes to the experimental results, the grasping under cavity pressure in the range of 0.1 and megapascal and 0.3 megapascal can be seen here for the lithium-ion battery. And additionally, the comparison of the experimental and numerical results for 0.3 megapascal of cavity pressure can be seen here. In this slide, you can see a demonstration of soft gripper integrated cobot system. Safe and sensitive grasping is provided using the developed soft robotic system compared to the rigid systems in automation. And we have used an embedded optical infrared sensor in this system. Here you can see the infrared optical sensor data up to 5-fold, which is embedded into the silicone layer. We have also measured the gripping force versus, and you can see the plot applied pressure versus gripping force here with our experimental setup for measuring of gripping force. Additionally, we also worked on the minimum required cavity pressure. The minimum required cavity pressure without dropping is 0.9 megapascal for this specific developed soft robotic gripper. And in conclusion, the grasping of lithium-ion batteries was achieved successfully using the additively manufactured soft pneumatic gripper with contact sensing, limiting both damaging and slippage. The Yale material model-based numerical results accurately predicted the experimental responses of the soft pneumatic gripper in the cavity pressure up to 0.3 megapascal. The control architecture is built with data from both exteroceptive sensing and FEM to accurately regulate the cavity pressure in the grasping task. In the future work, an enhanced multidisciplinary collaborative effort will be given to achieve in-field studies. Yeah, thank you.
Thank you for your presentation. Dear Parsim, do you have any question about the paper? Okay, no question. Thank you again. I wish you success in your career.
Thank you. Thank you.
Mr. Savaş Diliba. Next paper belongs to Said Esmaili. Dear Said Esmaili, are you ready to present? Okay. Dear Şifat Kayser.
Hello, sorry. I'm presenting. Can you see my screen?
Okay.
Okay. So I'm going to present the capstone project made by the students.
Please, you
for
have 10
students.
minutes, okay?
Yes, okay.
Okay.
Made by the students in the American University of Kuwait. Okay, so I'm going to present the project Averius, which is an effective, durable, and consumer-oriented solution to the locomotion problem in the virtual reality environments. Well, the concept of presence in virtual reality environments intends to erase any dissonance between the physical or the actual and virtual worlds. So the two environments are constantly synchronized and the virtual reality user feels no major differences between the two worlds. However, bridging the gap between the actual reality and the virtual realm is no easy feat. This is because in order to accomplish that, the virtual reality world must not only conquer all 5 senses of sight, smell, taste, touch, and sound, but it must also mimic real-world navigation and motion cues. Locomotion, which is the term used to describe moving from one place to another in virtual reality, can be said to be an important part of the immersion experience. Now, in recent years, the locomotion issue in virtual reality has been addressed through the development and refinement of unique omnidirectional treadmills that allow the participant to be more engaged and to walk smoothly and inexhaustibly in the virtual environment, which means to walk without constraints or the worry of hazardous obstacles in the real world. We want to highlight the different conceptions of what exactly nature means and to what extent our proposed system design and implementation will cross that threshold. To remind ourselves of this goal, we have named the developed locomotion platform after the distinguished Andalusian scientist Averius, who has contributed mainly to the fields of natural philosophy, physics, and metaphysics. Project Averius proposes to design and implement a locomotion platform entirely driven by a semi-natural and natural walking. So it also aims to mitigate cost and complexity, enhance durability, improve motion tracking accuracy, and build a core focus on user ergonomics in a consumer-oriented design framework. Now, for the design and implementation, the major aim is to precisely identify and anticipate the direction of movement in real time of the user's continuous gait as they walk on a concave, rigid, wooden, circular platform that will facilitate navigation in virtual environment. The final implementation and iterations included the concept of constructing a solid, reliable, and durable base that will not limit the user's motions. After the base was tested to provide for acceptable natural walking cues with the correct balance of inertia, its spatial performance metrics were evaluated, recalibrated, and refined. The system then encompassed more key components such as wearable technology. This involves sensors inserted into insoles for regular sandals modified to work in synchrony with the wooden base. The architecture and the design of this final product were derived from rough schematic plans. The height is 1.25 meters, width is 1 meter, and the depth of concavity is 20 centimeters. These measurements are generic and calibrated to suit any person's spatial performance in the virtual environment. So this is the architecture of the final product. This wooden base then would constitute the platform where the user will be able to safely interact with the virtual environment. This figure illustrates the equally divided sized section of the base's bedrock. And here we are outlining the base and the formation of the depth, which is 20 centimeters. The base was then covered with the standing board. This is again calibrated to suit any person's spatial performance in the virtual environment. So this is the final product, carpet, without the carpet inserts. The carpet inserts were then glued on top of the octagonal foundation to integrate the virtual sandal component of our wholesome concept into the system. Moreover, the system includes an Oculus Rift and a desktop monitor for integration between the software demo and the tangible hardware moving parts. The microcontroller used here is an Arduino Uno R3, which was chosen because of its availability and its suitability for rapid prototyping and continuous testing. In addition, we had two optical navigation high-end gaming sensors that were used to interface with the Arduino. The optical motion sensors are inserted in the soles of customized sandals that are embedded with the carpet sliders. The carpet sliders help the user smoothly maneuver about the base platform. This figure depicts a pair of placeholder test sandals that have optical sensors and carpet sliders inserted at their soles. We should also mention that several types of sandals were with different inertia ratings and insole material were tested and evaluated accordingly. So for the analysis, we were reading from the sensors were done by first examining the motion interrupt pin embedded in the sensors. When the sensors detect the motion, the pin is set, informing the Arduino that the values are ready to be read from the sensors. These values are 16-bit for both X and Y axis, 8 bits each of the detected motion. Next, the number quantity is evaluated using the counts per inch setting provided during initialization. These values represent the change in the direction detected by the sensors, ranging from 0 to 255, which are then outputted serially through the USB comms port of the Arduino. The software design of Unity was quite simple to integrate with Arduino using a serial controller called Ardity. Ardity allowed for simple X and Z axis manipulation. Full 360 degrees rotation was achieved using the Oculus Rift's native SDK. The Oculus Rift SDK permitted the creation of a virtual reality camera in-game that maps to the user's height and rotation. This allows for a seamless move for the user as now all aspects of the motion are covered. In addition, 2 virtual hands were added with the ability to use Oculus's recommended movement with non-natural locomotion that simply allows the user to move according to the joystick's position. But we were avoiding this method because this method causes nausea and motion sickness. But it was implemented to showcase the radical difference between the natural locomotion and non-natural locomotion sickness, allowing the user to experience both whenever they please. So this table shows the total budget breakdown. So the prototype, the whole project costed $1,645, where the wooden platform costed $750, The optical navigation gaming sensors were about $30 each, and the Oculus Rift kit costed $540. So the final product of our proposal integrated locomotion solution was assembled and tested successfully. The test subject were the sandals, stepped into the VR base platform. They placed the Oculus Rift harness and strapped the Arduino Uno R3 with Velcro fastener and proceeded to play the developed virtual reality game. So here's the subject, the test subject described an adequate level of immersion compared to traditional VR gaming experience. So here we can see the setup, the VR experience setup of the project Averios. So I will leave you now with the video presentation of the student demonstrating the project Averios, focusing on the creation or the construction of the omnidirectional treadmill and on tracking foot movement.
Hello, this is Nareem Diab from Project Averios, which is a senior capstone design project which focuses on creating an omnidirectional treadmill. So what we've implemented today is actually a sensor that tracks your foot movement tracks one-to-one foot movement in VR. So now I'm gonna put my VR headset on, and as you can see from the screen, which is basically what I'm seeing, is how natural it looks while walking. So as you can see in this demo, my hands are perfectly working, and then I can just take a simple stroll. All you have to do is walk naturally. You can of course change directions, and it tracks that too. We've also implemented a way to move using the joystick. However, this is what we're trying to avoid because this causes nausea and motion sickness. So what we're basically trying to demonstrate right now is how efficient and how less motion sick you'll get once you use our project. Hello, this is
Okay, so finally, one of the significant challenges faced was devising a way to prevent flex in the sandals. Due to the optical laser's functionality, it needed to be approximately 1 to 2 millimeters above the ground at all times in order to track movement accurately. So for that, there was two proposed solutions. One is adding a wooden support underneath the sole of the sandals to prevent the sandal from flexing, and the other one is adding a third carpet slider in the midsole to help prevent flex. That's it. Thank you for listening.
Thank you for your presentation. Dear participants, do you have any question about the paper? Okay, no question. I wish you success. Thank you again.
Thank you.
Next paper belongs to Said Esmaili. Dear Said Esmaili.
Hi, I'll be presenting instead of Dr. Said. Just let me, may I share screen?
Oh, okay, you can start. You can share your screen.
All right. All right.
You have 10 minutes, please.
Thank you. So good morning, everyone. This project was done in fulfillment of capstone project for the American University of Kuwait. It is named Pothole Patrol, an autonomous vehicle for locating and repairing potholes. So vehicular traffic has been rapidly growing over recent years, with more privately owned vehicles taken to the streets each day. Today, trucks weigh significantly more than ever before and are capable of carrying much larger payloads. The situation further grows decline of the roads. These factors, in conjunction with weather conditions, result in road damage in the form of potholes. This project was done in Kuwait, where the highest temperatures in the world are usually recorded. So this has a great effect on the asphalt and its quality. Potholes do not only cause damage to vehicle suspension systems, but may, in severe cases, result in serious accidents and permanent injury. And we actually had an incident last year where a gentleman was lost his life due to a pothole and a manhole cover damaged by the pothole. Another major problem is the process of fixing these potholes. Problems within the fixing process include multiple constraints such as convenience, area, and time consumed. Therefore, the availability of an automated machine that can perform all these tasks would be much more convenient and practical. The main objective of this paper is to develop an automated vehicle that is capable of moving uniformly on the street to locate potholes and road impairments. Once a pothole is found, a dispensing mechanism is initiated in order to fill that road cavity with some sort of road repair material or asphalt. To inform daily roadway users of the existence of the pothole, a software application is made to allow users to basically flag that pothole on a map. Another application is developed for the administrator side to provide them with any necessary tools to view and process the user requests. The system architecture of Pothole Patrol is shown in the following slides. It basically starts with a mobile application for the user and a mobile application site for the administrator's workstation. Both communicate with each other through a database server. When a user encounters a pothole while traveling on a roadway, he or she can report it by specifying the approximate location of the pothole using an integrated map on the application on the user side. Once a user specifies that location on the map, a request will be added to the database. Accordingly, the administrator will be able to view that request and deploy the repair vehicle to the location of the pothole. From here on, the administrator activates the vehicle through the workstation application, and the system operation will begin to try and fix the pothole using the machine. So here is a view of the system architecture. As you can see, the user activates the mobile application, flagging the potholes. The administrator can view that location and deploy the vehicle. And the vehicle itself is controlled via Bluetooth with the administrator's application. Components used: the RC tank car truck robot chassis. It has strong stability with 4 powerful motors able to deploy it on the road in rough conditions. The chassis has independent suspension shock, which allows it to run on the uneven road or surfaces given the size of the pothole. Arduino Mega specifications include 54 digital pins, 16 analog inputs, and a 16 megahertz crystal oscillator, a power jack for supplying the board with voltage, in-circuit serial programming header, and a reset button. Sharp IR sensors with high resolution with a range that varies from 4 centimeters to 30 centimeters. This is particularly needed to measure the size of the pothole. RC linear actuator. This is generally a powerful motor that is able to move a plunger in order to lift and lower the roller drum, which will be responsible for flattening the road and packing the asphalt. This is a general overview of the budget. As you can see, the actual hardware components and actuators are the majority of the price. The implementation: the user can control every aspect of the Pothole Patrol manually. However, there is an automatic option that manually starts and controls the process. If the option is chosen to automatically handle the process, system operation will begin, starting with a detection process, where the use of the IR sensor is required. The vehicle will begin moving forward while the sensor will perform continuous scanning, and the IR sensor will essentially keep tracking the distance from the ground, trying to detect the pothole. So the basic idea is to find the location of the road impairment as the car travels forward, which will allow the vehicle to then roll back so that it can be positioned over the pothole center. So it will detect the distance from the ground, and it will see from where does the distance start changing, detecting the road impairment. Once it reaches the end of the road impairment, it will roll back and go to the center of that road impairment or pothole. To record the exact distance required to reach the center, a counter is added to the Arduino code, so the robot will move discretely once it starts detecting the pothole. The counter will not increment unless a change in distance is detected by the sensor, therefore implying that the scanning of the pothole has begun. The vehicle will stop moving once it reaches the end of the pothole. Afterwards, the rollback operation will be initiated, allowing the vehicle to move forward for half the value that was obtained by the counter, hence essentially reaching the center of the pothole. After the vehicle is accurately positioned on top of the center of the pothole, the dispensing process will begin, which dispenses some form of asphalt or filler repair material to fill the pothole. The implementation of this process requires the use of multiple hardware components, such as the water pump, the dual relay board, and the IR sensors. Once the vehicle is centered, the repair material will be deployed into the pothole through a plastic pipe. In addition, the IR sensor will perform continuous tracking of the resin levels being poured into the pothole. The ideal distance, which is essentially the distance between the vehicle and any leveled ground, which contains no road impairments, is registered. So this is the ideally, you would want to fill up to that level. The values being received by the IR sensor are continuously compared against this ideal distance. If the two values become equal within some error margin, meaning that the level of the repair material is reached the level of the surrounding roadway, the dispense will stop. And finally, the process is to compact the material, which uses a roller. The main objective behind this process is to level the material that is being poured into the pothole with the level of the surrounding roadway surface. Once the roller is brought down using the actuator discussed before in previous slides, the vehicle will engage in a series of trips back and forth to level the material to the level of the road and compact the resin material. This is an overview of the hardware components and their integration. Of course, this is a general prototype. This is a bottom view of the vehicle showing the IR sensor. So this IR sensor would be detecting the distance from the ground and the pothole. To report a pothole in the street, the user would launch the application, enter their civil ID or any kind of their own identification into the main screen, pin the location of the pothole on the map, and then submit the request. An HTTP request containing that user's identification, latitude and longitude, basically the pin of the place on the map, is sent to the servers, and these parameters is used as saved in the database. When the request is completed, it will be deleted from the database. This is an overview of the user interface of the application, showing a user pinning the place of a pothole, for example. Of course, they can zoom in to get a more accurate pin. Future works, several improvements can be done upon this project to enhance its overall functionality, such as implementing a suitable mechanism for mixing resin material with water. So you would have more than one container and you would mix all these materials together before pouring them into the pothole. Incorporating a larger size pump that is capable of pushing repair material that is of higher density. So basically not all material can be pumped using all kinds of pumps, including some form of heating apparatus to heat the compact roller to create a better bond between the dispensed material and the surrounding roadway. So when the solid material is heated, it will have better bonding with the newly freshly added mixing material. So this is also in the future works. Thank you. Any questions?
Thank you for your presentation. Dear participant, do you have any question about this study? Okay. Thank you again. I wish you success in your career. Dear Ali Radi, will you present the next work? Next study?
Yes, I will. Let me just check.
Okay, you can start your presentation.
Just 1 second.
Said Esmaili seems to have been written as a speaker.
Yes. Just 1 second. Share screen. All right. Can you see the slides?
Yes.
All right. This is another project done by the American University of Kuwait in partial fulfillment of a Bachelor of Computer Engineering / Electrical Engineering. This is vGrip, virtual reality in a grip, essentially a tool to help people better interface with objects in virtual reality. Virtual reality and augmented reality are becoming an increasingly popular tool for education, training, and providing hands-on skills and entertainment. Usually VR focuses on the senses of sight and sound. However, touch for many applications is equally important sensory feedback. The use of touch becomes particularly essential in training applications to train pilots, astronauts, in military operations, law enforcement, medical research, planning, and rehabilitation. Virtual reality can be used when constant guidance is required for repetitive tasks. This can be seen with physical and mental health rehabilitation and training of patients in order to reintegrate them back into normal tasks while taking away the danger or social pressure. Maybe a person being still medically or having physical rehab may not be comfortable being in a social environment to practice a mundane task such as holding a spoon or playing with some objects. So they can do part of their rehab in VR to alleviate some of these dangers or pressures. Many of these applications involve the use of the hands, particularly grabbing and manipulating objects with varying degrees of force, need of accuracy, and need for feedback. The development of practical and portable systems to stimulate touch has not been explored as deeply. This becomes particularly important when the touch feedback needs to be informative to map certain tasks such as object manipulation, maneuvering, or for force feedback. Essentially, when you grab an object in VR, you would want some sort of feedback telling you that you have grabbed that object or how hard are you grabbing that object. vGrip is a human computer interface that utilizes a wearable exoskeleton glove to interact with VR and AR applications. It utilizes a wearable exoskeleton glove to interact with VR and AR applications. The glove stimulates the physical resistance of objects using motors and electromagnets. The glove enables users to feel the objects that they are holding within the VR environment. vGrip, along with the integrated VR environment, serves as a realistic low entry point to training. It also provides a more immersive experience for entertainment applications such as gaming, for example. The vGrip system consists of an integration between hardware sensors, actuators, and the microcontroller used, and of course, the Unity VR environment. There is a motion sensor designed by Leap that detects the motion of the user's hands and updates the location of the 3D model of the hand within the VR environment itself. Unity sends feedback, the Unity 3D engine sends feedback about the hand model's collision with the virtual object. It sends it back to the microcontroller, which activates electromagnetic actuators within the glove in order to restrict the user's hand movement, basically telling the user that, oh, you have already grabbed an object now, or you are facing some sort of resistance in the VR environment. This is an overview of the overall system architecture. As you can see, the Unity sends collision data to the microcontroller, which activates electromagnets on the glove, and the glove's position itself is detected by the motion sensor, which goes back and updates the location on Unity. The glove is a customized glove made of durable fabrics that consists of two main parts, the holder and the fingertips. And as you can see here, there are electromagnets to restrict the movement of the fingers. The holder contains 5 electromagnets. The fingertips are connected via strong threads that are passed through the electromagnets. The thread is passed in such a way such that it is in between a metal sheet and the electromagnet. When the electromagnet is activated with some sort of variable force, the finger's movement will be restricted by applying force on the metal sheet, essentially holding the thread in place, restricting the movement of the finger and the hand. The Leap motion sensor is used to provide precise tracking of hand movement as feedback to the Unity 3D engine. The motion sensor is flexible and can be set on a desk or mounted on a VR headset, depending on the user's convenience. The Leap hand model was customized for vGrip to allow detection of collision with the world object. Unity was used as the main processing software in which both the VR environment was created, collisions are detected, and decisions to switch the electromagnets were made. There are 3 main modules developed with the Unity engine: the hand 3D models with its physics engine, collision detection, and a serial controller to interface with the physical glove, as well as virtual objects to be played with in the VR environment. Colliders were created within the Unity 3D engine to detect collision detection between the hand model and the VR objects. Colliders have a primitive shape such as just a box or a sphere, a cylinder or a cone, depending on the model of the VR object, specifies the kind of collider that should be used. Colliders are constantly monitored for events and interactions within the VR environment. When a collision occurs, it gets registered in a list. The list is aggregated for all the fingers and palm colliders and then sent serially to the microcontroller. This is a view of the collider model visualized within the VR environment. As you can see, the fingertips colliders are modeled by spheres and the palm is modeled by a box. In order to test the implementation, a simple maze game was made. The game utilizes the V-grip system in every part of the game, including the menu, where instead of clicking the button, the user pulls a button instead. The game consists of multiple mazes where the player has to grab a stick and maneuver it through the maze from start to end without the stick touching the edges or the walls. Completing the game requires some form of accuracy of the use system, comfort of the user, allowing them to focus, and immersion within the VR environment. Such a game can be used as a physical rehab purpose for users and patients who are still trying to get back control of their hand. This shows the game application where the user attempts to solve the maze. Once again, the user has to move that object through the maze without touching the sides. So it requires some form of finesse. So here is a small video showing students demoing the V-grip system. Yes, it's just music. It's okay. There's not much to hear. So as you can see here in the demo, it's moving with the in the virtual environment, and shortly he will attempt grabbing an object. Yeah. So as you can see, he's grabbing an object in the virtual environment. And manipulating the cylinder. So. All right, so in conclusion, in our future work, the electromagnets used for the project are not incredibly strong. However, they are safe and robust and easy to change. For example, if you use motors and if you apply too much force, you can break the motor. While here, the point of failure is the thread. And if the thread cuts, that's easily changed even by the user, and it does not require a technical skill. As future work, a stronger magnet is needed in order to exactly stop the hand from the desired amount of time and release it at will. Using a wearable microcontroller instead of a regular one in order to enhance the user experience. Interfacing with other VR engines such as the Unreal Engine, not just the Unity 3D VR engine. And thank you. Any questions?
Thank you for your presentation. Dear participants, do you have any question about this paper? Okay, no questions. Thank you again. I wish you success in your career. Dear Shifat Kaiser, are you ready to present?
Yeah.
Okay, you can start your presentation.
Can you see it?
Yes. You have 10 minutes, please.
Yeah, okay. So I'm Shifat Kaiser and I'm studying Masters in Electrical and Electronics Engineering at Karunis Technical University. And our today's topic is model-based detection scheme for denial of service attack on lane keeping system. And these are the outlines of my paper. Introduction, modeling, where I will be discussing vehicle model, lane keeping asset model, and denial of service attack model. And there will be detection of DOS attack, results analysis, and conclusion. So introduction, we all know that one of the most essential things to affect the present automobile sector is vehicle safety. And to contribute in this, several features, autonomous vehicle features like adaptive cruise control, lane keeping system, lane departure warning, accidents detection, anti-lock brakes, and smart parking systems, traffic signals recognitions are there and they have been introduced. And to control these features, we need some new technologies, and those are GPS, artificial intelligence, machine learning, and several sensors like radars, cameras, and leaders. So all these features are in the big name, which is ADAS, Advanced Driving Assistance Systems. So with the introduction of intelligent transport system, we have seen that the intravehicular communication has improved a lot, and as because there are more features, and so there are more sensors. As a result, there are more networks and communication, which makes the system more vulnerable. Because the interconnectedness leaves some loophole for the cyber attackers, which makes the system like this. So this is the way to distract the whole transport system as well as jeopardize humans' lives with some casualties, accidents. So we'll be discussing about the detection of denial of service attack on especially the lane keeping system. This is the modeling. So at first the vehicle model. The vehicle model, to model this, we used a bicycle model for each of its axes. These are the parameters, and the input of the vehicle is the steering angle, and the output is the output is the lateral velocity and the yaw rate. And these are the parameters we have used to model the vehicle. And yeah, we modeled all our system in the MATLAB Simulink. This is the lane keeping assist. So to model the lane keeping assist system, we used some sensors, and they sense the lateral deviation and the longitudinal velocity, curvature of the road. And then they are sent to the lane keeping assist system model. And the lane keeping assist system provides the necessary steering angle to the vehicle. The denial of service attack model. So the denial of service attack actually occurs when the user loses control over the device because of data absence or packet loss in the communication systems. Though there are several kinds of device attack that can happen, and but in our system, where you can see here the red mark, we actually apply the attack on the actuator. So after the control signal, the attacker manipulates the control signal and send it to the vehicle with some delay. And this is the detection of our denial of service attack. And here the motivation is that the vehicle will store the reference, and it will take the reference using the offline map, and it will put the destination, and it will calculate the steering angle by using GPS and calculating the yaw angle and lateral deviation. And then it will then compare with the current steering angle with the stored. And if it satisfies this condition, then it will continue to compare. And if it doesn't, then it will alert the driver, human driver, to take over the control. So these are the results and analysis. So this is our lane curvature, and from at 12 seconds, we can see a continuous change, constant change till 20 seconds. And to overcome with this curvature, we have a steering angle changing like this. And here is a small change at 12 seconds to 18 seconds, which we cannot see here, so we can see here. So this thing is actually taken as the reference and will be later on compared with the current one. And we have some scenarios. We actually implemented delay like 0.1 second, 1 second, 3 seconds, 6 seconds, and 8 seconds. And we checked if our detection scheme is enough robust to handle these attacks. But yeah, it was quite nicely it handled the attack. So these are the results, and with a 0.1 second delay, you can see the differences with the red one. It's the current steering angle, and the blue one is the stored steering angle. So there is a delay of 0.00016 radian, which is negligible, but we later on can see that our detection system can still detect it. And this is this is the delay with 1 second, where we can see a much change of 0.00068 radian. And with 3 seconds, we can see it's 0.00022. And with 6 second delay, we can see 0.024, which is much higher than the others. And if we continuously increase the delay time, it will continue to show more haphazard conditions, and at some stages it can go unstable. And yeah, it also can change on the timing range. Maybe if we can see if we make the attack before 10 seconds or 8 seconds or after 18 seconds, the results will differ from like this. So these are the detection system. So our detection system detects the 0.1, 1, and 3 seconds delay at 12.5 seconds, as we have given that if the current steering angle changes 5% above or less than the reference, then the detection system should work. So according to that, our detection system, it starts alerting the human driver at 12.5 seconds till 15.9 seconds. And in case of 6 seconds, it detects, it puts on the alarm from 12.5 to 16 seconds. And at 8-second delay, we can see that it doesn't stop, only between 0.3 second it stops here. But yeah, it continues to alarm for 20 seconds. And so it will stop the detection when the driver take control over the vehicle. Yeah, so the conclusion, so we could see that the attacker makes the system follow the previous signal by delaying the control signal in the controller to the actuator communication system. But they can also do it on maybe sensor to controller or system to sensor system. But wherever they want to attack the system, they can. But our detection system will work fine with this. And it created small and negligible differences, which the driver may not focus, but our detection system was able to alert the driver. So the result of the paper also shows the effectiveness of the detection scheme, which can work under different uncertainties. Yes, these are my references, and yeah, thank you for your attention.
Thank you for your presentation. Dear participants, do you have any questions about this paper? Okay, no questions. Thank you again. I wish you success in your career.
Yeah, thank you so much.
Dear Yevgeny Dmitriev, are you ready to present?
Yes, I'm ready.
Okay, you can start if you want.
Okay, I share my screen. Okay, can you see the presentation?
Yes, please, you have 10 minutes.
Okay, thank you. Good morning. I'm Yevgeny Dmitriev, a PhD student from the University of Pavia in Italy, and I'm going to present the paper named on cobot programming in industrial task, a test case. The developed robotic application will be presented, focusing on the relevant details of the industrial and offline deployment of a collaborative robot. After the process details are described, the robotic cell layout is revealed. And the main reason for using a collaborative solution highlights the programming key points with respect to the features proposed by the literature. The structure and the characteristics of the final program are analyzed to detect the challenges as well as the advantages of using a collaborative programming approach. And finally, the conclusion will be drawn. Let's consider how the collaborative robots are defined. The robots are those machines that improve the efficiency and automate the low value added manual processes while simplifying the work and reducing the injuries, since they can execute all the boring, dangerous, and non-ergonomic tasks. With respect to a special purpose machine, the robots work safely in a reduced footprint cells and allows to readjust the program to fit the process variation. Typically, the industrial robots are quick and accurate. They can be deployed in fixed place with fixed task and provide a high level of quality. These robots are suitable for productions that for production processes with large batches and little variability. However, The collaborative robots are smaller and lighter and can work near people with minimal or no safety fences. This is thanks to the high number of sensors and the built-in force control that the collaborative robots have. They are easy. The cobots are not intended to suppress the well-established industrial robotics. Instead, they represent an alternative solution in specific cases, since they target a different market, foresee different end user, and are developed for basically a different set of needs. The traditional robots require a lot of knowledge and time to program an action. Because of easy setup and programming features, the cobots are easy to program, and usually they have user-friendly software and can be quickly implemented in a process. This makes them more flexible for quickly changing processes. Since these intuitive interfaces and user-friendly robot programming are studied in many academic researches, we want to fill the gap in presenting the industrial collaborative application. We want to highlight the relevant robot programming phase and the structure of the program. The robot programmer has to conceptually develop and optimize the robotic cell, select the sensors to be used, and foresee the interactions methods to allow an easy modification for the final program. However, we have to consider that the final robot user may not be the same person that has that programmed it. So we should allow to easily alter this program, and although many programmers may find the intuitive, user-friendly methods tedious and limiting with respect to classical text-based programming, they have to use them to open to a more collaborative programming involving the operators in a customization process. To do so, the programming phase has to foresee the following steps. First of all, the initialization step with respect to the identified process to be automated. Then the authoring phase, which involves the robot in program creation from scratch. The authoring scope that contextualizes the program. The programming robot capabilities have to be taken into account with the corresponding programming method, and the programming features have to be chosen wisely to allow further editing and debugging phases and the verification. To do so, we'll focus we will present the characteristic of the authoring phase, identifying the process, showing a layout design and the robotic features and technologies that we have used, and the program design development. So the robotic case study proposed in the present work is an end-of-line unload of capsules to seal the wine bottles. These are produced by an automated industrial machinery, and they may have different sizes, different shapes, and a complex decoration on them. They are stacked in rows of 60 to 80 items, depending on the setup of the machine and of the size of the project. And the manual operation forces the operator to pick and place those rows whenever they are ready into a plastic tray. The tray may be of 6 or 7 slots because of alternative requirements of the output pallet. The fillet trays are stacked on the pallet in such a manner to reduce the height and to avoid product damage. Since the items have to be have to be displaced are completely different, and the rows of capsules are smaller and have different size and shape with respect to the trays, we have foreseen to use 2 different grippers. The robotic manipulator that we decided to use is the Omron TM12, which has a built-in vision system, a force control capability, and can be programmed with a visual flowchart-based language. The 2 grippers are one with the 4 vacuum caps and jigs for robust couplings with the surface of the tray, and the other one has 10 vacuum caps, smaller, to be able to pick up the row of the capsules. The proposed layout can be seen in the figure on the right. Okay, can be seen in the figure on the right, and we can see the labels which explain the layout. The label number 1 is for the feeding pallet of empty trays that have to be picked and placed on the pallet 2, that is the output pallet. The number 3 is a position for discarding those trays that are not respecting the alternating of 6 and 7 slots. Number 4 is tool change station, and the robot is able to exchange the grippers before going to the label number 5, where is placed a conveyor belt buffer, which is attached to the machine that produces those capsules. The proposed layout has been firstly designed and simulated through use of RoboDK simulation software, and this way was possible to verify the reachability of all the relevant points and the robotic cell. The robotic cell layout has been schematized on the right. The program is designed to have 2 main routines of pick and place of trays and capsules, 2 gripper chains, and 2 more supportive subprograms. The generated program seems to be quite easy unless we don't consider the practical programming features that are quite challenging, especially if the program has to be general, flexible, and understandable. The decision tree, to code the decision tree can be a substantial effort, especially when the number of decision and error cases is quite large. Programs often have several logical decisions to make, such as when and how many times to repeat an operation. An example to distinguish between the first run of the cycle and to restart from an unknown state are quite challenging to code in a visual programming language. There also have to be considered the interaction with other devices and how to handle error conditions, like how to react to failures in picking and releasing the parts. All these cases raise the complexity of any programming method, and in our case, even if we have used the TM flowchart-based programming language that actually improves the overall readability and already simplified the structure of the robot programming, as we can see on the picture on the right, we can easily recognize the variable checks, the recovery gateway, and the task recalling. However, this is the initialization process, the initialization program, which can explode if we consider a pick and place of trays. An example can be very much complicated. And to overcome these complications, we have to program some more features that are the nesting, lean loop management, parallelization, and the branching for the conditional instructions. The developed subtask of trace displacement is depicted in the figure, and it is characterized by a large number of logical elements which are necessary to correctly pick and place the items, perform the necessary errors checks, and place the tray in the right position. The built-in vision system, the built-in vision system can be seen in branches 3 and 4, which are for the bar recognition applied to each tray, and the sonic depth sensor for moving to pick the tray, and the force control nodes are easily identifiable in the procedure, while remaining clearly differentiated the single branches that correspond to parts of the logical procedure of the subtask. So a clear organization of the branches is mandatory for any further modification of the task. The following enumeration can be followed to identify each function, the function of each group. To program the collaborative robots open to collaborative programming. So considering that the simplification of the programming method may not simplify the overall deployment of a collaborative robot in an industrial environment. So the initial effort for an industrial task remains high, even if we use these simplified methods. However, if we use those features of parallelization, nesting, and we clearly define the branches that define each robot motion, it is required a little effort to understand the existing program and to be able to modify it. So at the end, the industrial task of palletizing process was developed, and the features of the task were described, and the challenges have been highlighted considering the recent research of simplified robot programming. This increased security for future works can be considered for applications that paves the way for menu optimization and process quality and cell layout, so unlocking the possibility to close human-robot interactions. Thank you for the attention. Do you have any question?
Thank you for your presentation. Okay, no question, I think. Thank you again. I wish you success in your career.
Thanks.
Dear Ali Mahdi, are you present?
Yes.
Okay, you can start your presentation.
Okay. This is Ali Mahdi from Atlantic University. We're going to talk about reciprocal altruism-based path planning optimization for multi-agents, supervised by Assistant Professor Dr. Muhammad Omar Khan and co-supervised by Assistant Professor Dr. Poland Erfanoglu. Encountering the problems of nature that has always been a challenging task. What makes it more difficult is the change in operating condition over time. A robust algorithm needed able to track the continuously changing optima over time. A novel particle swarm optimization algorithm based upon population kinship connectivity is proposed with the intent of improving the performance, introducing the sharing of particles information. Algorithm named as reciprocal altruism-based particle swarm optimization, RIPSO, utilizing kinship relatedness between particles during the optimization process to reciprocate the significant data regarding the landscape. The term reciprocal altruism presented by Trivers to clarify altruism between particles that are unrelated is that helping another individual in expectation of receiving help in the future. Establishing sociobiology by Wilson depicted as the focal hypothetical issue. How can altruism, which by definition reduces personal fitness, possibly evolve by natural selection? The particle swarm optimization, or PSO, in past decade, the theory been growing rapidly as PSO. Many application of several problems has been utilized. It imitates by the behavior of animal societies that don't have any leader in their gathering, like fish schooling and bird flocking. Ordinarily, it is discovering sustenance by arbitrary flock. The potential solution is with particle that has the nearest position. Then all members will follow with help of communication among members. Hence, flock accomplish best condition at the same time. With pointing the cap with the proposition, utilizing the concept of reciprocation, RIPSO, ensure all particles remain in close contact through information exchange. Amount of information that is exchanged depends upon physical placement in the search space regions. Depending on regions, particles either classified as donor or recipient, the amount of information that is exchanged monitoring through their associated health indicator. The benefits of introducing this indicator will be highlighted through comparison between proposed approach and canonical PSO. The proposed approach starting initializing particles, then the proportional altruism model, which is we proposed in 2 circles with the same center but different in radiuses, first and second region, and the rest of the space as the third region. Third, generate particles template, and then reciprocal altruism particle swarm optimization, RIPSO, which is calculate or update the position and cost of the particles, then determine the recipient and donors of these particles, which we proposed the center of PAM regions as it is the best personal particles position in the swarm. And by specifying the current fitness level as it's the minimum cost value of the swarm, the RIPSO algorithm encourages all the agents for reciprocal altruism to minimize the waste of fitness level by keeping the farthest agent closer to the optimized one as much as possible. All simulation of altruistic distribution produced an altruistic investment. The patterns of distribution of altruism among kins were affected by the change in value of the model parameter from one region to another. It provides the opportunity for the rest of the agents to settle down and ensure their place in the vicinity of the optimized agent. Result and discussion. Altruistic investment produced by all simulation-based altruistic distribution. As the situation mentioned, the cost of altruistic would be great enough to offset the recipient modest benefit. With the change of value of model parameter, the distribution's patterns of altruism among kin will be affected from region to another. And because of the procedure that we tend to use, here we reached optimized best cost in less than 23 iteration with 64 particles. As we can see in our simulation, that all the particles will be close to each other in the first and second region, and the optimum and the optimal position of the current position of the particle will drag all the particles to the first region in order to be in a close condition to the optimum position. We can see particles region distribution from the first iteration to the 23 iteration. That's it start with 64 particles in the first region, then jump to the second region, then jump to the third region, and from the fourth iteration to the 12th iteration. So the proposed approach dragged all the particles to the first region again effectively in a 12th iteration. We can see that reciprocal altruism between second and third region, that we have this particles in the blue in the second region and the recipient particles in blue in the third region. So we have in the 6th iteration, 7th, 8th, and 10th, 11th, we have donors from the second region to the third region in order to drag them to the second region. Then we have this reciprocal altruism between first region and second region. So we can see that we have in the 4th iteration, donors from the first region to the second region, which we have in blue recipients. So we have in the 4th, 5th, and 6th, and 9th, and 12th iteration, we have altruism between the first region and second region in order to drag them again to the first region. And we take a sample, particle number 8, in order to determine the distance to the center before and after the altruism. As we can see, it's from the first to the third iteration, it is inactive. Then it is decreased from 17 to 7. So it is a recipient in the fourth iteration. Then in the fifth iteration, it is a donor. So it can be extended from 15 to 19. Then it is be a recipient in the sixth iteration. So it's reduced its distance from 24 to 4. Then it will be inactive to the last iteration. This is the distribution of particles and distance to center comparison between RIPSO, which is our proposed approach, and canonical PSO. As we can see, the distance in red, which is canonical PSO, is more than distance from the RIPSO, and it is like that to the last of iteration in the 3 trial. So in our proposed approach, we have reached 0 or the optimum position in the 23 iteration, but in the canonical PSO in the 3 trial, it is not. We can see the distribution of particles comparison between RIPSO and canonical PSO. So it starts with 64 particles in the first region, then jump to another region. So we can see that particle of canonical PSO in the third region more than the RIPSO. And we can see in the 20 iteration that we have particles in the second region, but we cannot have any particles in the second and third region of the RIPSO from the 13th iteration to the last iteration, to the 23 iteration. And we have a particle in the third region in the 22 iteration for canonical PSO. So that will be sorry. So that's approved. Our RIPSO is going effectively as compared to the canonical PSO. As a conclusion, a novel optimization algorithm with explicit reciprocal altruism is proposed for working on path planning, namely reciprocal altruism-based particle swarm optimization, RIPSO. It can quickly find the particles that are far from the optimized path to tweak them after evaluating its scenario according to a kinship relatedness with the change of 2 conditions of that particles. First, enforce particle to come closer to the optimized one. Secondly, health indicator is updating itself based upon its distance from optimized path. A conclusion, utilizing the healthy particles of the search space to guide them to the promising point and avoid wasting fitness area, ensure better connectivity and information sharing by health indicator and optimized movement of the swarm. The performance of the proposed approach shows that reciprocal altruism has played its role effectively in order to control the movement of the swarm along the optimized path. The simulation result proved that RIPSO outperforms the canonical PSO algorithm both in terms of error reduction and the close connectivity. The future work, recipient quantities should be more as if it's compared to the donors, and improvements must execute with the kinship relatedness coefficient to ensure a wide range recipient altruism. Controllability lost from particles went far with the less than 20% health status. No obstacles exist in our search space. These are our references, and thank you. Ready for questions.
Thank you for your presentation. Dear participants, do you have any question about the paper? Okay, no questions. Thank you again. I wish you success in your career.
Thank you, appreciate it.
Dear Marin Zilewski, are you ready to present? Dear Marin Zilewski. Dear Miko, will you present the study? Dear Miko, can you hear me? Okay. Yes, the first session of the symposium is over. Dear participants, I would like to end the session. I suggest you to attend the next session, which will start shortly at 1:30. See you. Goodbye.
Hello.
Marin Zilewski?
Yes, I'm here.
Okay. Are you ready?
Yes, one moment.
Okay, you can share your screen.
Do you see the presentation?
Yes, please, you have 10 minutes.
Yes, thank you. Hello, my name is Marin Zilewski. I am Associate Professor in Technical University of Sofia. I will present you the paper, Analysis of Mechanical Operation in a Type of Machining Centers. The machining centers with computer numerical control are highly automated machine tools capable of performing multiple mechanical operations on different surfaces of the process workpiece. This is a wide variety of construction, dimensions, and automation degrees of these machine tools. In general, they can be classified into 3 types based on their structure, namely horizontal, vertical, and gantry ones. The horizontal type is a machine where the spindle to which the cutting tool is attached is mounting horizontally. The vertical type has the spindle set upright, and the gantry type has a gate-like structure with the spindle mounted on the gate sailing facing downward. The multiple mechanical operation place high demands on the respective electric drive system, require an optimal selection of motors, power converters, sensors, and mechanical gears. The drive systems of the study machine include feed, spindle, and auxiliary drives. A general algorithm for selection of electric drive system for CNC vertical machine center is offered in another publication. And mathematical modeling and computer simulation offer effective ways to study the drive system in different tangent in steady state mode of operation. The programmer logic devices are an appropriate option in the control of the auxiliary drive thanks to the useful hardware description language like Verilog HDL. The main requirement to the machining center can be formulated as follows: power capability and machine rigidity, machine with the shortest possible tool overhang on the spindle, position control of the feed drive, coulomb support in machining, automatic tool changing, high spindle speed and torque, optimal energy consumption and productivity, automatic work, no vibration to achieve desired hardness, possibility for firm clamping of the tool. The aim of this research is to combine optimally the respective mechanical operations and tool use for minimal consumed energy and maximum productivity. The methodology applied includes a theoretical approach and an appropriate experimental study. The result obtained can be used in the practical implementation of the considered type of machining center. The studies in this work focus on a type of CNC machining center with the next parameter. The construction is vertical, type of control is computer numerical control, number of axes is 5 control axes. Possible technological operations are milling, drilling, boring, reaming, engraving of different inscriptions. Type of main movement is rotation. The drive system is the most important part of the machine tool. It carries out the cutting processes as it affects the quality of work pieces, such as accuracy, roughness, energy efficiency, and productivity of the whole machine. A simplified block diagram of the drive system for the study class of vertical machining center is illustrated in Figure 1, where the following notations are used: is CNC is computer numerical control, ED1 to ED10 electric drive, G1 to G8 mechanical gears, L1 to L8 volt. The drive system must be chosen optimally to meet the requirement of various mechanical operations. The selection in this case has been made through the different methodologies, taking into account the spindle and feed speed, turkeys, and powers. Feed drives are linear for axis X, Z, and Y, and rotary axis A and C. The linear axes are used for positioning of a work table and the tools in the desired place depending on the workpiece. The rotary axis realized with rotary table give opportunity for angular positioning of the workpieces. Position control algorithms are applied for this drive to achieve the required accuracy and trajectories of movement. For the studied class of machining center, an appropriate speed control for the spindle drive is used. A programmer logic device with developed quadrilateral diagram is implemented for the respective auxiliary drives. Basically, the machining operation depends on the type of a machine construction, the geometric shape of the workpiece, the type of tools, and price. They are related to the machining parameters, namely spindle and feed speeds, turkey and cutting power, cutting depth, and others. The machining centers enable the process of milling, drilling, boring, and reaming. The appropriate approaches of determining the basic machine parameter in the individual operation are similar. This paper presents the determination of parameters of milling process. Table 1 shows the step for determination of the cutting power and turkey, and the basic notation are as following the next slide. The input data include hardness of the process material in the other parameter like cutting diameter and working increment and cutting depth. The different milling method determining the type of machine used for 3, 4, or 5 coordinate 1. The selection of tools depends on the process material and workpieces. The cutting powers is divided between the feed drive and the spindle drive respectively. And the machining time can be determined by the equation 1 in the slide, where the parameter Lm is machine length. The practical application of a studied CNC vertical centers is illustrated with machining of a specified steel workpiece. Usually, several types of mechanical operation are required to obtain the desired geometric shape. For the full realization of geometric shape, the following mechanical operations are passed secondly with the developed geometric model and generate paths are presented in figure 2. Figure 3 shows the processes of rock milling in A and fine milling in B for shaping for the overall dimensions of the workpiece. Figure 4 demonstrates both drilling processes with different diameters. Figure 5 illustrates both milling processes for shaping the upper parts of the workpiece using a rock mill with different diameter of 0.025 and 0.008 meter. Figure 6 shows the machine workpiece after the presented technological processes. Figure 7, 8, and 9 in the next 2 slides illustrate some theoretical results reporting the tool life, the cutting speed, and the feet per revolution received with online cutting speed calculator. Figure 7 presents a diagram for the milling of a steel workpiece at different cutting speed. Figure 8 and 9 present charts for drilling of steel as the cutting speed and feet per revolution are studied. The received parameters in this case are tool lifetime is 66 minutes and tool life length is 38 meters. The presented example illustrates the different types of technical operation in the studied CNC vertical machining centers. In conclusion, the main features of a type of vertical machining center with CNC are described. Based on the analysis mechanical operation in this machine, an appropriate drive system is presented. The aim of this study is to combine the respective mechanical operation applied in the tool use for minimal consumed energy and maximum productivity. The research methodology used includes a theoretical approach and a suitable experimental study. The practical application of the considered machine tools is illustrated by the coordination of the respective drives based on the developed geometrical model using the Aspire software. The machine workpiece is of a specific steel type. It is processed by applying the necessary mechanical operation for realization of a geometric shape. The research carried out and the result obtained can be used in the modernization and implementation of a studied type of CNC machining center. Thank you for your attention.
Thank you for your presentation. Dear participants, do you have any question about this article? Okay, no question. Thank you again. I wish you success in your career, dear Marian Zalewski. I want to thank you all the participants. See you in the next sessions. Goodbye.
Goodbye.